Hey, Francisco. Can you hear me okay?
Yeah, I can hear you, Jesse. Hello?
Perfect. All right. So we are going to start on number 5, right?
Let me check. Let's see. Number. We did number 3, right?
Well,
Oh
number
no,
3 was
yeah.
correct
No,
already.
sorry, number 3. Number 3 was right. Yeah.
Yep. And then we did 4, and then we didn't get a chance to do 5 yet.
Yeah. So 5.
So 5, we're given a function, a rational function. R of x is x minus 9 times 2x plus 3.
Mm-hmm.
And then all of that over, we have x squared plus 2x minus 2.
Mm-hmm.
And they're asking us to find the x-intercepts of the function. So what I like to do is to draw a picture to get a better understanding of exactly what we're trying to do. So the basic graph of a rational function is going to look like this. So we're going to have one asymptote or multiple asymptotes on the x-axis. That would be instances of infinite discontinuity, parts at certain x values that aren't part of the domain. And then we also have for vertical asymptotes, or I think I mentioned vertical already. We also have horizontal asymptotes. So they're asking us to find the x-intercepts. So the x-intercepts are going to be the place where y is equal to 0. So this would be an x-intercept. This would be an x-intercept. They're easy to find graphically, but you know how to find them algebraically. Do you know a method that we can use to get that information?
For algebraic quadratic formula.
Well, this has a quadratic. And if we distribute the numerator, we'd have a quadratic over a quadratic. But that wouldn't exactly help us find the intercepts. I mean, if it were just this function right here, without it being a rational function, if it were only x squared plus 2x minus 2, we could use the quadratic formula to get the information. Absolutely. But
Well, that graph represents a rational function of the graph. The one that you just showed out. Okay. Yes.
So the 2 points I highlighted here and here, these are the two x-intercepts. So that's what they are out graphically, but then let's talk about how they're represented algebraically. So we know that this is the place where y is equal to 0, or f of x is equal to 0. And then same thing with this one. So that means, if we call this a, that means f of a is equal to 0. And if we call this point b, that means f of b is also equal to 0. So our job is to find a and b. Or our job is to find the values of x that make this whole thing equal to 0. So to find the x-intercepts, we're going to set the function equal to 0. And then we want to solve for x. So and at this point, once that I've set something equal to 0, I tend to just get rid of the function notation itself to make it a little easier to understand what we're doing. So we're trying to solve for x. Notice how x appears in a lot of places. We have an x here, and here, and here, and here. So it's a little bit tricky to solve for x because there's so many of them, but it can be done. So how do you think we should go about this? Like, what would be a good place to start if our goal is to solve for x?
So we said that we're trying to solve for x.
They want us to find the x-intercepts, and setting this equal to 0 and solving for x is how we manage that. That's our general strategy.
So what are we trying to solve for? Oh, okay. I see. F of x equals 0, and solve for x. Okay.
So we've already set it equal to 0, and now we just want to solve for x. How do we want to start that process?
Divided by 0? I mean, no, plus 2.
So things would be a lot easier for our purposes if we didn't have this denominator right here. So can you think of a way to get rid of the denominator? So then we only have this on the left side of the equation.
Uh-huh. Mm-hmm.
So how do we eliminate that denominator? How do we get rid of it?
Mm-hmm. Divide? Would you divide by?
Well, you're close. We're dividing by something already. So what's the opposite of dividing by a polynomial?
Multiply.
Perfect. So we're going to multiply by the polynomial that we're currently dividing. So let's multiply x squared plus 2x minus 2 on both sides. That'll make it no longer a rational function. We'll only have one single quadratic to deal with. So then we simplify. So what's on top here is going to cancel with what's on the bottom here. And then 0 times anything is just 0. So the right-hand side is still going to just be 0. So let's rewrite this. So we have x minus 9 times 2x plus 3 equals 0. So things look a little bit more manageable now. When we had a rational function, it was kind of confusing as to what we wanted to do. But now that we've simplified it this way, it's a little more clear in how we solve for x. So do you know what we want to do after that? If our goal is to solve for x, our goal is to figure out what x has to be for this equation to be true. How do we solve for x?
Let's see. Solve for x. Because I know there's two x's on both sides of the
Not both sides. I think you mean both factors, right? And this factor and this factor.
Here, let me think.
So let's treat
And
each
9 on
factor.
both sides by 9 on both sides. Divided.
It's actually a lot simpler than even that. So let's look at each factor. So I'm going to look at this factor right here, x minus 9. So I know that if x is equal to 9, that would make this 0 because 9 minus 9 is 0.
Is that 3 over 2?
Yeah, it would be negative 3/2.
Yeah, negative 3 over 2.
Exactly. So these are the two x values that'll make the whole function r of x equal to 0. So we solved for x and we got these as our solutions. So an x-intercept is a point. Remember, the x-intercept is the location where the graph crosses the x-axis. So our first intercept is going to be 9, 0. Our second intercept is going to be negative 3/2, 0. So on your test, this one would be C.
Yeah, question C.
Any questions?
Yeah, because no, because I knew it was C because I put none at first, but I knew the answer was C, option letter C.
So how'd you know it was C?
I'm sorry?
How'd you know it was C?
Because of the step that we were doing was where we had to solve for x, and then we graphed it with the rational function, which is x minus 9 over 2x plus 3.
So you factored it just like we did just now, and maybe you got positive instead of negative.
That's what I did. I did the work for it, and then, but I did on a separate paper. So, and it gave me on the x-intercepts of the function r. Okay. Okay.
All right, so it looks like our next circled one is 7. So it says, which of the following is not a factor of the polynomial function below? So we're dealing with factors of a polynomial. We have f of x is equal to 5x to the 4th power minus 8x to the 3rd power minus 16x. Oh, I forgot 13x squared. Sorry, so it's going to be plus 13x squared. And then minus 16x plus 6. So we have some choices here. We want to pick which one is not a factor. So this one is kind of difficult because we have 5 terms here. If it were an even number of terms, we'd be able to factor by grouping. But because this is something with 5 terms, we can't use that method here. So we're going to do something else. We're going to do something called the remainder theorem. Have you heard of that?
Yes, I've heard of it before.
Remainder theorem. So the remainder theorem tells us that if a certain value of x gives us a 0 as a result when we plug it in, that means that value provides us with one of the factors of the polynomial. So for example, if we plug in 2, for example, and we get 0, that means that x minus 2 is going to be a factor of the polynomial. So let's take this term by term. So our first factor that they give us for choice A is x minus 1. So if x minus 1 is a factor, that would imply that f of 1 would be 0. So we can test that right away. So let's plug in 1 for x and see what we get. 5 times 1 to the 4th minus 8 times 1 to the 3rd plus 13 times 1 to the 2nd minus 16 times 1 plus 6. So let's simplify. We get 5 minus 8 plus 13 minus 16 plus 6. So that would simplify to, hang on a minute. We get 0. So we just figured out that f of 1 is 0, which means that x minus 1 is a factor.
Right.
So if we were to make a list of all of the factors of f of x, x minus 1 would be one of them. All right, so let's try another one.
So we haven't still gotten the answer yet for.
Sorry, what was that?
We're still on question 7.
Yeah, we're still on 7. Okay, so we tried choice A. We figured out that that is a factor. So let's do the same thing for choice B. So we're given the binomial 5x minus 3. So they are implying that if this is a factor, then there would be a certain value of x we get from this that would make the entire polynomial equal 0. So add 3 to both sides and divide by 5. Solving for x gets us 3/5. So if f of what this, sorry, I can't talk right now. What this tells us is that if f of 3/5 equals 0, then that means 5x minus 3 is also going to be a factor. So let's test that real quick. And it's going to be a little tricky just because we have exponents and we have fractions involved here. In fact, I might just use a calculator just because of how hairy the arithmetic is going to get. All right,
Okay.
so can you see my screen?
Yeah, I can, yes.
All right, so we're going to plug in 3/5 for x and see if we get 0 as a result. I'm going to make sure that's right. So the coefficients are 5, -8, 13, -16, and 6. Okay, that's good. And then the exponents are 4, 3, 2, and then 1. That part is also good. And then we have 3/5 for everything. Okay, perfect. Let's see what this evaluates to. Okay, it is 0. So that tells us that the original binomial that they gave us is also going to be a factor of the factored polynomial, a factor of f of x. So let's try the next one. So we have x squared plus 2.
Right.
So this is going to give us imaginary numbers, because if we subtract 2 from both sides and then take the square root of both sides, we're going to get negative square root. We're going to get the square root of 2i. But it might also resolve to 0. So we can test this one as well. So back to the calculator. I'm going to just replace everything with, what was it again? It was square root of 2i. Or I times square root of 2. Same thing. See what we get. So we also get a 0 for this one. So that means another factor of the polynomial is going to be x squared plus 2. So that would leave only that last option. So the first 3 are factors, which means that x squared plus 1 would not be a factor. So it's D for this one.
Okay.
So do you have any questions on what I did there?
So how did you get D?
Well, we figured out that the first 3 choices are factors, which means the 4th one is the only one left. So that would be the one that's not a factor. Just process of elimination.
Okay. So it'll be option D. Okay. Question A, I got correct. That was easy. Number 1.
Okay. So
I showed my work. I showed my work for it. Sorry, no. I showed the y and x intercept, but I said that I need to show work.
Okay. So we're given the rational function, r of x is equal to, we have negative x squared plus 5x minus 6. All of that is divided by x plus 2. Okay, so we want the x-intercepts and the y-intercepts. So remember that the x-intercept is the place where y is equal to 0. It's the place where it touches the x-axis. And then remember that similarly, the y-intercept is going to be the place where x is equal to 0. This is the place where the graph of the function touches the y-axis. So let's start by finding
the
y-intercept
0.
Sorry, what was that?
Is the y-intercept 0, 3, 0, -3?
How do we know for sure?
Because I graphed it x squared plus 5x minus 6. I graphed it on the calculator.
Okay. that it's good that you know how to do that, but let's also do the same thing algebraically. It's good to know how to do things multiple ways. So the y-intercept is the place where x is equal to 0. So let's take our function and plug in x for, or 0 for x. So r of 0, we have negative 0 squared plus 5 times 0 minus x, and then minus 6, and then all of that is divided by 0 plus 2. So upstairs, we have 0 plus 0 minus 6, downstairs 0 plus 2. So yeah, this is negative 3. So you got the right answer, but you also want to know how to do it algebraically. And this is how we do it. So we plug in 0 for x and see what we get as a result. So when x is 0, we found out y is negative 3. So that is our one and only y-intercept.
Yes.
So how did you find the x-intercept? What method did you use?
The x-intercept?
X-intercept or intercepts. There might be more than one. I see you got 1, 0. So how'd you get that?
Same thing. I graphed it as well.
Oh, okay.
But I want to learn the algebraically way because you said it.
Okay, so that is actually really similar to what we just did with the y-intercept. Do you have any questions on that?
No, it's just I want to know. So it's the same thing how we did on that we got the y-intercept of -3.
It's very, very similar, except this time we're plugging in 0 for y instead of a 0 for x. So this right here tells us that y is equal to 0. So we're going to write this as 0 equals negative x squared plus 5x minus 6 divided by x plus 2. So we have a rational function. We have a quadratic divided by a linear function, and we want to solve for x. So how do we accomplish that? How do we solve for x in this equation?
Solve for x?
So it's tricky because x appears in multiple places. It's here with the second degree, and it's here, and then it's also in the denominator. So just like last time, can you think of a way to kind of get rid of this denominator so we only have the quadratic to deal with? So this is a quadratic divided by x plus 2. So what's the opposite of dividing by x plus 2?
Multiply.
Perfect. So let's multiply both sides of the equation by x plus 2. Just like we did in the last problem or a couple problems ago. So it simplifies nicely. 0 times anything is still 0, so that doesn't change. And then on the right side, the x plus 2 on top cancels with the x plus 2 on the bottom. So to rewrite this, we have 0 is negative x squared plus 5x minus 6. So instead of a rational function, now we just have a simple quadratic to deal with. And by this point, we've had a lot of practice with quadratics and how to solve them. So this one has something interesting about it. So notice how the leading coefficient is not just a 1, it's a -1. So can you think of a way to manipulate this so that it's a positive instead of a negative?
Positive.
We want positive x squared instead of a negative x squared.
You switch the signs as plus x squared.
Yeah, exactly. So let's multiply both sides of the equation by -1. That'll flip the sign of everything and keeping it equal to each other as it was before. So 0 times -1 is still 0. And then if we distribute the negative, we get positive x squared, negative 5x, and positive 6. So now we have a positive leading coefficient, which is exactly what we wanted. So what method do we want to use to solve the quadratic here?
What method?
Our goal is to solve this quadratic for x. What method do you think we should use here?
Are we trying to solve for x again?
Mm-hmm. Exactly.
Okay. Um,
So graphing is one way, but can you think of a way to do it
yeah.
algebraically?
Can you either set something equal to 0?
So yeah, that is what we want to do. And luckily we already have that. So you can see how we set the quadratic equal to 0. So that is a very good idea, and we've already done that.
Yeah. Would you also factor as well?
Exactly. I think factoring would be the best way to do this. So the quadratic formula would always work no matter what the nature of the roots are, but like factoring is so much faster and so much more efficient. So if you can factor, you definitely should. So let's try to factor this. How do we factor it?
Would be minus x plus 2.
Sorry, you cut out a little bit. What did you say?
Minus x plus 2.
How did you get minus x plus 2?
Because if you look in the top, it says minus x, and then plus the squared, which is 2.
So remember, the strategy for factoring is to find two factors of 6 that also add up to our middle coefficient, also add up to -5. So what I like to do is I like to list out all of the factors off to the side.
Oh, okay.
So factors of 6, because 6 is the constant at the end. That's what we want to multiply to. So factor pairs that make 6. We have 1 and 6, -1 and -6, 2 and 3, -2 and -3. So as you can see, Francisco, we have 4 different pairs of factors that multiply to 6, but only one of these pairs is also going to add up to -5. Do you know which one?
That add up to 5?
Also adds up to -5.
3 and 2?
3 and 2? Well, 2
Sorry,
plus 3.
-2 and -3.
Exactly. So do you remember what we want to do now that we have the winning pair?
Sorry, you put out. Can you hear me, Tim?
Oh yeah, I can hear it. So I just asked, do you remember what to do now that we have this information?
What is after?
Sorry, what was that?
So what is after?
What do we want to do now that we know that these two numbers multiply to 6 and also add up to -5? So the question is, what do we want to do with those? So it's okay if you don't remember. What we want to do now is put them into the factored form. So our first number is -2, so our first factor is going to be x minus 2. And then what's the next factor going to be? Any ideas? Hey, Francisco, are you still with me? Can you hear me okay? We might be having technical difficulties.
Hello?
Hey, can you hear me okay?
Yeah, can you hear me?
Yeah, I can hear you.
Hear me now?
You're cutting out a lot.
Yeah, same with can you hear me now?
Oh yeah, I can hear you. Can you hear me?
Yeah, I can. Can you hear me?
Oh yeah, I can. Yes. Okay. So we got our first factor. So remember what we're trying to do. We're trying to factor this quadratic, and we're about halfway there. We got our first factor, and we're trying to figure out what the second factor should be. Do you remember how to get the second factor?
I'm trying to
So if -2 got us this factor, what do you think this next one should be?
three?
It will be x minus 3. So you're right.
Yeah, it's -3. Yes.
+3 will get us is one of the solutions.
Minus.
I know exactly what you mean, because if x is 3, that would be a solution. So yeah, I totally get what you're saying. Same thing with x is equal to 2. So we found the two x-intercepts. And so it's good that you know how to graph this to find the solutions. And now we just got the same thing algebraically. So our x-intercepts are going to be -2, 0 and -3, 0. All right. So this would be the answer to the next part. These are the two x-intercepts. Any questions?
No, I assume I get it now. 0 is, yeah, so I see how we get the minors, the x-intercepts. How much time do we have left?
We have about 20 minutes.
An hour, 30 minutes?
Yeah, an hour and 30. We've already had an hour and 4. No, we've already had an hour and 10. So we have 20 minutes left.
Okay.
Right. Ready for the next one?
Okay.
Can I erase?
Yes. Yeah, I got it.
All right. So for the next.
So we're going on to B.
Oh, it's the same function, so I don't need to erase everything. They want us to identify all the asymptotes.
Identify all the asymptotes. Yeah. Yes.
So do you remember how to find the horizontal asymptotes? Can you hear me okay? Are you still here?
Sorry, can you say it again? It keeps cutting out my mic. It's weird.
Oh yeah. I just asked if you remember how to find the horizontal asymptotes.
How to find the asymptotes?
How to find the horizontal asymptotes.
Yes.
What is that process like? How do we find the horizontal asymptote?
Is that the leading coefficient, right?
So the horizontal asymptote that is a result of scaling up and down. So you know how you can have a function and add 1 and 2, or add a constant at the end to move, kind of translate it up and down on the y-axis? So that is one method to tell what the horizontal asymptote should be for this function. But there's another way too. So remember that we can also analyze the end behavior of the function to tell what the asymptote should be.
Yeah.
So we're going to use the end behavior method because it's foolproof and you'll always be able to use it. And it gives us a lot of information about what the function tends to as x gets really, really big. And this is just like the concept of the limit from calculus that we talked about last session.
Can you hear me?
Oh yeah, I can hear you. Can you hear me?
Okay. Yeah, I can. Yes. Making sure. Okay.
So I want to get a sense of what this thing kind of looks like to understand how to proceed. So I want to find the y-intercept first. And actually, I think we already found that. Yeah, we did. So when x is equal to 0, we get negative 1/3. So we have a point right here. And we also had x-intercepts at -2 and at -3, right? Sorry, I erased it, but are these the intercepts we had before?
Yeah. So oblique asymptote y equals x plus 3, horizontal equals 9, and then.
Oh no, it's 2 and 3. My bad. So it's not -2 and -3. They're both positive. So we have an intercept at 2 and at 3. So that tells me the function is going to look something kind of like this. So this is a rough idea of what the function is going to look like. So we can tell from the picture that we're going to have no horizontal asymptote, but we will have an oblique asymptote, and we will have a vertical asymptote. So how do we figure out what the vertical asymptote should be?
What do you say? Horizontal asymptote?
Well, we found out that we don't have a horizontal asymptote, but we do have a vertical asymptote. Do you know how to find that?
Horizontal asymptote?
Sorry, can you repeat that?
Horizontal asymptote?
Yeah, exactly. We don't have a horizontal, but do you know how to find the vertical asymptote?
Oh, so we're talking about horizontal asymptote.
Well, we were, but now we're talking about vertical.
Oh, okay. So vertical asymptote.
Mm-hmm. Do you remember how to find that?
Yes.
How do we do that?
Do you the denominator equal to 0, and then you will solve for x, right?
Perfect. Exactly right. So what do we get when we do that?
And then the vertical asymptote is equal to x is equal to -2.
Perfect. And that is kind of consistent with my drawing. So I know I'm not very good at drawing, but we can tell, we can glean from my drawing that at least it is a negative value that gives us that. So vertical asymptote VA, x is equal to -2, because that's the value of x that would make us have a 0 in the denominator. And then for, we don't have a horizontal asymptote. So HA, horizontal asymptote, would be none.
Yeah.
So do you remember how to find
oblique asymptote?
Do you remember how to find
What's
that?
Find
Do you remember how to
vertical
find
asymptote or
Whoops. Can you hear me still?
can you hear me?
I can
Yeah.
hear you.
So what's the question again?
Do you
What is
remember
what?
how to find an oblique asymptote?
Yeah, I do.
How do we do it?
Divide the numerator by the denominator.
Exactly. So you can use synthetic division or polynomial long division. I'm more of a fan of long division, so I'm going to use that.
Synthetic division?
You can use synthetic, but I just usually use a polynomial long division because the steps just make a little more sense as to what we're doing and why. So synthetic division would also work, but I'm going to do long division in this case.
Yeah,
So
long division.
Let's start. So how many times can x go into -x squared? That would be -x. because negative x times x is negative x squared. And then negative x times 2 is negative 2x. So just like with normal long division, we multiply and then we subtract. So this is going to be 0x squared. And then this is going to be plus 2x. So 5x plus 2x is 7x. Bring down the minus 6. Actually, we don't have to do that yet. Okay, so x can go into 7x 7 times. So 7 times x is 7x. And then 7 times 2 is 14. And now I'm going to bring down the negative 6. So now we subtract. 7x minus 7x is 0x. And then negative 6 minus 14 is negative 20. So we have a remainder, but the remainder doesn't matter in this case. The remainder doesn't impact the oblique asymptote. The only information we need, Francisco, would be this right here. So this result is our oblique asymptote. So remember that horizontal and vertical asymptotes are just singular values. So for example, a horizontal asymptote could be like y is equal to 2. A vertical asymptote is also a single value. Like x is equal to negative 2, that's a single value. But an oblique asymptote's not like that. An oblique asymptote is always a linear function. So this linear function right here, negative x plus 7, is our oblique asymptote.
Okay. So wait, isn't oblique asymptote, because I got y is equal to x plus 3.
Sorry, can you repeat that?
For the oblique asymptote, is it x plus 3?
It should be negative x plus 7 because that's what we got for the long division result.
Minus x plus 7. Okay, yeah. Yeah, I got that. So minus x plus 7.
Y is equal to negative x plus 7. So yes. It looks like for part C, you got that one all the way right.
Yeah, I got 6 out of 6 on that one.
All right, so let's move on to number 2.
So, how much time do we have left? Like 15 minutes?
We got like 9 minutes left.
Okay.
We had the half hour from before, and then we're going 8 to 9.
Okay.
So for number 2,
okay,
we're given the polynomial function f of x is equal to 2x to the 4th power plus 2x to the 3rd power. And then we have minus 11x squared plus x minus 6. And then we want to figure out the maximum number of zeros that this polynomial can have. So have you heard of something called the fundamental theorem of algebra?
Yes, I have.
What does that tell us about a function? So what is the fundamental theorem of algebra? What does the fundamental theorem of algebra tell us? What is it? Do you remember? It's okay if you don't, but do you?
Yeah, I have it somewhere in my notes. I do have that. Is a polynomial equation of degree n with complex number coefficients has roots or solutions in the complex numbers.
For the sake of time, I'm just going to summarize it real quick. So it tells us that the number of complex zeros or roots of f of x is equal to the degree of f of x. So remember that a complex zero includes real zeros and imaginary zeros. So for example, if this is one of the factors, this would be a real zero. And then if we have another factor like this, then an imaginary factor would be like I times square root of 2. So complex zeros include real solutions and imaginary solutions. So the fundamental theorem tells us that the total number of complex zeros is equal to the degree. So what is the degree of this polynomial?
The degree?
Mm-hmm. Do you remember how to identify the degree of a polynomial?
How to find the degree of a polynomial?
Yeah. The degree of a polynomial is going to be the highest exponent present. So our leading term is 2x to the fourth power. Our highest exponent is 4. So the degree of this polynomial is 4.
Mm-hmm.
So the degree is 4. So what that tells us is that this polynomial f of x is going to have 4 complex zeros. And I want to show you something real quick. So can you see my screen?
Yes.
Okay, so I graphed the polynomial in Desmos. So we have 2 real zeros. So -3 and 2 are the real zeros. The fact that we have a degree of 4 means that we're going to have 4 complex zeros. So we have 2 real ones, and then we're also going to have 2 imaginary ones that we can't tell by looking at the graph. So 2 and 2. Whoops, didn't mean to do that. Okay. So our answer for part A, it's going to have a maximum of 4 zeros because the degree is 4.
Maximum of 4 zeros. Can you hear me?
Are we ready for the next one?
Yes, so it has a maximum of 4 zeros.
For part A, yes.
Yes. Okay.
And then part B says, use Descartes' rule of signs to figure out how many positive real zeros the function can have. So do you remember Descartes' law of signs?
Descartes' rules of signs?
Yeah, Descartes' law of signs, or rule of signs.
Yes, the number of positive zeros in polynomial function f of x.
Yeah, you cut out a little bit there. Sorry, what did you say?
Is it positive real zeros in a polynomial function f of x?
It has something to do with that. And we want to look at the nature of the coefficients to tell us the nature of the real zeros. So if we want to look at the signs of the coefficients. So our coefficients in this case are going to be 2, and then 2, and then -11, and then +1, and then -6. So we want to examine the places where we change signs. So we go positive to positive. That's not a change in signs. And then we go positive to negative. So that is a change. Negative to positive is also a change in sign, and then positive to negative. So we have 3 locations where this changes signs. And then from there, let me try to remember what to do because it's been a while since I've seen this. I apologize.
No worries. Was B correct, 1 or 3? I can't remember how I got that.
So in this case, yeah, it's correct. So we get the 3 because we have 3 sign changes. And then we get the 1 by determining if this is an odd function or an even function. So we do the same thing by plugging in -x. So 2 times, instead of x to the fourth, it'll be -x to the fourth. And then instead of 2x cubed, it'll be 2 times negative x cubed. And then negative 11 times negative 11x squared plus x becomes plus negative x. And then the negative 6 is unchanged. So we can simplify this to be 2x to the fourth. And then it will be plus, or no, sorry, it'll be minus 2x cubed. And then we have, this will be minus 11x squared minus x, and then minus 6. So we're going to do the same thing we did with the original function. We're going to count how many times the signs of the coefficient change. So coefficients of this new function are 2, -2, -11, -1, and -6. So let's count how many times the sign changes. So we go we go positive to negative, and then negative to negative, so we don't count that. That's not a change. Negative to negative again, that's not a change. And then negative and negative for a third time, that's also not a change. So we only changed the sign one time in this situation. We changed the sign 3 times in this situation. So that's how we know that this can have 1 or 3 positive real zeros. That's what Descartes' law of signs tells us. All right, so that takes us right to the end of the hour. So before we wrap up for the evening, do you have any questions?
No.
All right, well, in that case, I think your mom said we'll be meeting at the library on Thursday at the same time, 3:30. Is that good with you?
Yes. Yeah, same time.
All right, perfect. Well, I'll see you on Thursday and enjoy the rest of your evening, Francisco.
Okay, you have a good one. Have a good night.
Thanks, you too.